Now we're on to our next session. It's my pleasure to be speaking with Kurt Meinke. Kurt is a spatial analyst and cartographer, and he's also a trainer and teacher and author. He earned a Master's of Geography from the University of New Mexico. In early 2021, Kurt moved from the United States to Denmark and now works for Septima in Copenhagen, Denmark. He has published his 10th QGIS book, collecting field data from QGIS and Mergent Maps with local press. In 2015, he became an OSGeo charter member. He is also a fellow of the Rewilding Institute and a board member of Wild Arizona. It's a pleasure to work with Kurt. He is one of the leading researchers and designers of spatial analysis for the Nature Conservancy and a lot of environmental organizations on hand. I'm going to share my screen here quickly, and I'm going to begin with the first part of this presentation. So our title of our talk is Landscape Scale Watershed Planning for Beavers for Biodiversity and Climate Change. So this is looking at the landscape scale of Michigan, Wisconsin, Minnesota, and what's referred to as the Laurentian Forest Province. So the Superior Bioconservancy mission is to protect and restore the biodiversity integrity and hydrology of the Great Lakes region and the Laurentian Forest Province throughout Minnesota, Wisconsin, and Michigan. So we're looking at ecosystem services, evolutionary processes, and I would like to refer to this as sort of a healthcare plan for this bioregion of the planet. So here we are in the upper left side corner of the organism that we all live on, Earth. The region on a flat map here is this green area, which is this Laurentian Forest Province. So this is a continuous north woods. And the yellow area shows the watershed of Lake Superior, which is one of the focus areas we have also. It's also a high carbon region across this landscape. So the North Woods, as it extends, it doesn't have a lot of population, especially in the Upper Peninsula, Michigan, and Northeast Minnesota. Protecting Lake Superior is one of the goals of our organization, and protecting that hydrology with beavers is one of the things within that watershed that can be achieved. So we're hoping to have that as one of the primary goals. Where this positions in the United States, this is also the headwaters. If you can see my cursor here, this is all the rivers of the upper Mississippi and then Great Lakes here. So the focus of our region is this inside this yellow line. So this is a type of wellhead protection for North America. And it's also this headwaters of North America in many ways. It also has a tremendous amount of public land, and it's a big recreation area. So the Boundary Waters is up in here. Quetico is a beautiful area, the BWCA in Northeast Minnesota, the Upper Peninsula of Michigan. And then, so this is all this public land outlined in these areas for camping and farming. It also has a very important layer of usufructuary rights, which are the tribal rights that extend over this, that we believe in upholding and honoring and recognizing. So this usufructuary means to hunt and gather upon those lands. And the federal government has an obligation to maintain all public lands, which is 21 million acres, to sustain and maintain those rights. It's also had the largest recolonization of wolves in North America. So this area back in 1973, there were about 200 wolves in Northeast Minnesota, and now we have about 4,400 wolves. So the wolf has a very important feature for the health. And in the Ojibwe's origin story, their fate is somewhat tied to the wolf, and their word for him is Mahingan. So we know also that wolves trigger a lot of behavior in white-tailed deer, which is the primary herbivore in these forests. And so with too many deer and no movement. So there's been a lot of research showing how by deer being influenced by a prey relationship with wolves, that the trees are healthier. So the forest is healthier. So white cedar, Canadian hemlock, or hemlock and Canadian yew sometimes disappear when there's too many deer. But those things regenerate. So they're very important for the health of overall forests. So the other keystone species, of course, is beavers. And so this fundamental natal hydrology that they did gave us a type of stream morphology, a type of resiliency, and also providing water quality, stable quantities, biodiversity, and flood mitigations, and climate resilience, such as what Emily was speaking about earlier. So in pre-settlement, we had all the beaver ponds that were in North America. So if we think of 1491, all the rivers look similar to this. So it's like a string of pearls of beaver ponds on it. And this is in northern Michigan by Ishpeming. And this is a slide actually where I'm actually above this slide, the same area. So you can see the canals, the dams, but there's so much more volume of water being held here and retained because that beaver structures have completely, in essence, flooded this area and maintaining these wetlands. And the wetlands that are there are these are the wetlands we have on our landscape are sort of a relic of what was there in pre-settlement. And so Glennis Hood did some studies and showed that you can get up to 8 times as much water. You're getting this infiltration in the groundwater. You're getting upwelling seepage. So you're getting stream complexity and stream health. So it's a structure. So what happens when the beavers come in is they may be first one down, but they start to put more of this structure in and make that complexity. And each of those pieces is another filter for the water. And this is up in by the Pikes Creek, which just was on one of our sponsors. Picture was taken about 10 minutes apart. And you can see how the erosion and this is all roiled up. So these beaver ponds work like speed bumps and they slow the water down and they basically, this water's running clear, this one's running like coffee. So they have two functions that they somewhat do. It's sort of like a sewage treatment plant as well as a storm detention pond. And those features are really important for climate change, for flooding. So I worked on a study with University of Wisconsin and Milwaukee Metropolitan Sewage District. And in it, in one area, we showed that by placing 52 hypothetical dams upstream in the Milwaukee River watershed, we could lower peak flood levels, in some cases 40%, high 30%, and we take thousands of homes out of floodplains. So this system, one of the questions was, well, how much water? So we did measure, Dr. Lau, who's a hydrologist and engineer I worked with, he measured how much water could be stored in that, and it basically came up to 1.7 billion gallons. So in terms of stormwater ecosystem services, the agency that paid to do the study would value that at $3.3 billion. So how does this work? Basically, you're getting this additional storage of water. So it raises and pushes that water down into the water table. But you're getting a tremendous amount in what is called this hyporheic zone. And you'll have, with that, you've got this water being stored. So with biodiversity being a crisis going on, we need to move on to, let's get this going. So so you can kind of think of the watersheds as the fruit of the watersheds are these beaver ponds. And so the benefits are stream structure, stable biodiversity, flood reduction, and climate resilience. And we will see this benefit across the landscape if North America changes its beaver policy for all the waterfowl. And this is northern Wisconsin. So this hydrology is the system that we're looking at here. And Kurt's going to be showing this mapping where we took all this public land, we looked at linkages between it, and he used a technique to bring it together. And so this high carbon forest eventually is one of the things that we need to look at for our own self. So it's about 33% of the land is actually public land. And what Kurt is he's showing the connective tissue between it. And so what he's going to show is how we determined where these different channels of connective tissue, so to speak, of corridors are originated through a technique of mapping and global observation. So it's my pleasure now to turn it over to Kurt.
Thanks, Bob. Let me share my screen here. Okay, so my section of this talk is modeling this big word, omnidirectional biodiversity connectivity. So again, this is the study area which Bob introduced. It's essentially the Laurentian mixed forest province, including parts of Minnesota, Wisconsin, and Michigan. And our goals at the outset were to identify what's known as structural connectivity, so not species specific, but structural connectivity across the landscape, weighted towards riparian corridors. And specifically, we wanted to identify omnidirectional connectivity, so not simply corridors, which I'll introduce in a second, but rather getting the qualitative look at connectivity for every pixel in the landscape. And we wanted to therefore identify linkages that connect public forest lands in this study area. We can then use this data to prioritize areas for protection and hopefully engage citizen scientists to conduct on-the-ground research on priority watersheds, and in the long term, incentivize protection of linkages by selling carbon offset credits for private parcels. So a little bit of linkage modeling 101. I don't want to get too deep into the weeds, but there are numerous methods of modeling connectivity, and they all use this thing called a resistant surface. So I'm going to quickly cover some of the theory around connectivity modeling to explain why we chose the method we did. So what is a resistant surface? Well, it's a data set where every cell value reflects the energetic cost or the difficulty for a critter to move through the landscape. And so in this is a good image to visualize how the resistance raster works. Areas in red represent more resistance to movement, and areas in green are easier to move through in this case. So here we have a simple scenario where we have wildland block A and B, for which we want to model linkages between. And here we have a resistant surface where cells that have a high value are the most resistant, and cells with a low value have a low resistance. So one historic method of doing this is called least cost corridor, or least cost path rather. And this technique identifies the least cost path connecting these two wildland blocks. So it's not necessarily the shortest path, but it's the least costly. And the downside is that this solution is only 1 pixel wide. So in our case, 30 meters. And this doesn't really represent the complexity of the natural world and the reality that there may be multiple linkages connecting these two areas. So there's another related technique called least cost corridor, which widens that a bit more, but we still kind of have this problem where we have just one solution and a kind of a narrow solution, and one that doesn't really represent reality. So well, it represents reality, but not the complexity of the natural world, I'll say. So we use this software called Omniscape, which is used to produce maps of omnidirectional habitat connectivity. And this was developed by the Nature Conservancy, and it's built on this software called CircuitScape. And it's really useful for modeling connectivity in landscapes where you don't have discrete cores or A and B points that you're trying to model connectivity from. In other words, you want to model connectivity across the whole study area. So this is a sample of the results of an Omniscape analysis where you have in bright yellow and orange the corridors of the linkages, but you also end up with areas that are kind of large, homogeneous connective regions, and then you have the more classic corridors or these kind of dendritic looking linkages in the landscape. So for our analysis, this is the resistant surface we use, and when you're zoomed out, it doesn't look like there's that much detail going on, but when you zoom in here, you can see that there is in fact quite a bit of detail at the local level. And so here we have the result of the primary output, and this is called cumulative current flow. So each pixel here has a value representing the movement potential through it. So the areas with the highest connectivity are in green and lowest connectivity are in red. And so again, our analysis is done with 30-meter pixels, so we can zoom in quite tightly to see in this inset where there's a riparian crossing or there's a bridge across a road barrier connecting both sides of the road. So here's the area around the Keweenaw Peninsula, which is quite interesting. It includes a large area, kind of in this mid-purple color here, that is a large homogeneous area with high connectivity. And so we call these areas core reserves, where it's not a classic corridor, it's just a huge area where there's generally high connectivity throughout the whole area, kind of a wild area. Here's the area south of the Apostle Islands, which shows numerous linkages connecting these national forest parcels. So to me, this represents the true complexity of the natural world where it's not simply one corridor between wildland blocks. There's multiple strands of varying qualities and widths that connect these areas. And the results are qualitative, so we can identify critical riparian road crossings shown here with these red markers, where we have a road, which is a barrier to movement, and there's bridges undercutting the road here, and so that forms an important linkage. So we also did a watershed beaver analysis. So we expanded an older study to the bigger study area that I showed, and we computed statistics by several watershed scales, including the potential beaver population based on stream miles and land use, and then things like the percent wetlands, percent forest, percent beaver suitable vegetation. So for every watershed, we calculated these statistics. And that allowed us to start mapping um, the potential beaver habitat by watershed. So we have it at 3 watershed scales. So these are the coarsest watersheds, about 670,000 acres each, and in dark green showing the highest beaver population potentially. This is zooming into the next level of watershed, about 70,000 acres each. And then we have this all the way down to the finest available sub-watersheds, about 20,000 acres each. And to make this data useful to everyone, we have created an interactive web mapping site with all of this data. And we designed this to be simple to use and easy to navigate. So I'm going to tempt fate here in a second and try to do a live demo of this. But before I do that, we also aggregated all the connectivity linkage statistics by the watershed level, so that we could compare watersheds by both their connectivity metrics and their beaver metrics. So I'm going to get out of PowerPoint here and go online. And here we have the connectivity map. And so this is an interactive map, so I can zoom in and zoom out and pan around. I can toggle layers off and on. So here I'll turn on forests and protected lands. And so I can also use this function up in the upper left to find and zoom to a particular sub-watershed. So for example, I could type in Briar Hill and zoom into this watershed. And as I zoom in, more data, more layers become available. So now I'm seeing the barriers to movement, major highways, and I'm also seeing there's a critical linkage right here, crossing here. I can turn off this landscape permeability layer and turn on this other one, which classifies that into critical, high quality, and medium quality linkages. So we can see that this is a critical linkage that the model identified here. And I can search for other watersheds. To show you some more functionality in here, I'm going to search for Silver River. And we have like 3,000 sub-watersheds here. So sometimes you have to go through and choose which Silver River you want. I'll start with Houghton County. It zooms me into this. And what I can do with this Silver River watershed is click on it and get a pop-up that shows me the metrics of what's in that watershed. The size of the watershed in acres, the potential beaver population, which is quite high. And then you can see that most of the area is core reserve. And so it's not surprising that often we find now that a watershed that has potential high beaver population also has a lot of connectivity within it. If I turn on core reserves, we can see that this whole region is core reserve. And I can now go to the other Silver River watershed to compare. This Silver River watershed also has a lot of potential beaver and also has a lot of connectivity. And now to show you some of the beaver data, we have this companion site. And I can, this one is a little simpler. It just has the beaver data by watershed, but I can search this for Silver River and go to that same one I was just looking at. And when I click on this and this site, I get more beaver-centric data. So I still get some data on the linkage acres within this watershed, but the rest of it is all beaver-centric, potential beaver population and percent beaver suitable vegetation. And we can really start to, look at the situation in these different watersheds. Here's the other Silver River, which also had a high beaver population, but we can see that this one has a lot of impaired streams in it, streams that don't meet the various levels of the Clean Water Act and don't have a restoration plan in place yet. And so you can really start to do a lot of interesting, you kind of, if there's a watershed you're interested in, you can zoom into that and get a lot of hard data and statistics on that particular watershed and compare it to neighboring watersheds. Let me go back into PowerPoint. Bob, I don't know if you want to discuss the applications of this and jump in here.
Well, the organization, Superior Bioconservancy. Thank you, Kurt. This tool that Kurt has put together for us is really, I think, the most cutting edge in scientific and makes it very accessible. So one of the important features, we want to have this available to everybody in this region as a conservation planning and policy development tool, and so that they can make informed decision making and we can have sustainable land use. But also this for education and awareness, public engagement as an educational resource. So we're in the process of developing this. So this will be live on our website. And so in terms of the environmental impact assessments that can happen, whether it's a pipeline or a mine or solar development, something, this tool could be available as to mitigate some of the development impacts and also to require environmental regulatory compliance. So as we are analyzing and we have this tool to work with climate and address climate change, this can give us a more resilience system and tools for the public to engage agencies or corporations that we have ecosystem services preserved. And Kurt, I'd like to also just to perhaps also, we hope this will support conservation organizations and promote ecotourism. And there's cultural values that are tied to indigenous people here. We want to have collaboration with community and indigenous rights as an empowerment for public to engage agencies for better planning.
So yeah, that is the analysis and the tool. We've developed a lot of data, and I can post the links to both of these sites into the chat so people can look at them. The connectivity site is still a little bit in beta. There'll be some changes coming to that. It'll get a little nicer to look at. But there's a ton of data and thought that went into these analyses. It's been going on for about a year now, and so this is kind of the coming out party for this analysis, and it's exciting to share it with everyone.
Yeah, we don't have it yet on our website yet because we have to. Kurt's company is integrating it to us so that it becomes accessible for the community and for land trusts. This is a very valuable tool to look at connectivity in terms of land purchases on public policy between the policies that are also on the public lands we have. As I said, there's 21 million acres of public land in this landscape that we're mapping here, and this tool can be applied across the Midwest and the United States and other places. So please do copy and paste these ideas to your region to improve our capacity and abilities to handle the questions and the problems that we're going to have with climate change and also just foreign policy going forward for stability. Let's see what we have for terms of questions in the side here.
Bob, you want me to help you with that?
Yeah, please do.
Okay, so I think the biggest question is, how much work is it or how easy would it be to transfer this tool to other states and regions?
Well, I think the answer to that is, well, if you wanted to replicate this methodology to another region, You definitely need to have someone who is GIS savvy to develop the data and work with the software. But it's certainly doable, you know.
Um, Bob, are you guys working with to partner with the Canadian watersheds to the north, or are you only working with the United States?
The intention is to work with Ontario and the Canadian government to, especially for Lake Superior's protection of that watershed. At this point, it's really an issue of capacity. It's a pretty big, 100,000 square miles is, a large area to look at public policy. And so we're looking for partnerships with other local groups throughout the whole Midwest and in the Upper Great Lakes, as well as the Canadian government. So at this point, we have not done that connectivity. Most of the area in Canada is still pretty much contiguous forest. So the more development threats there are lesser. They're not existent, but it's well, we do hope to do that.
And a little more on that. This was started out as kind of a proof of concept, and there's data issues. So there's issues when you're working across international boundaries to get data sets that align on both sides of the border, so that you can have apples to apples. And so we didn't want to wrestle with that while we were developing this proof of concept.
How does your tool compare with the BRAT tool, the Beaver Relocation Assessment tool that other people are using?
Well, our potential beaver population data is a fairly simple formula based on stream miles and land use, but I don't think BRAT takes into connectivity at all. So I don't think there's anything really in BRAT from what I remember. But honestly, it's been several years since I've looked at that that models connectivity in this way. This is a fairly unique piece of software, this Omniscape.
And does the tool work in urban areas? Like, can you see omnidirectional connectivity in urban landscape between public parks?
Oh, absolutely. Yeah. Um, you can, you can zoom into Green Bay or Duluth, and you can see where the software identifies small corridors of the importance of local stream networks and parks in an urban setting for connectivity. Absolutely. So since it covers the whole area, you're going to find the biggest connectivity in the wilder areas, but there are certainly important linkages in urban and suburban areas as well.
Okay, we have a question. Are all the GIS tools open source?
They are actually. I'm an open source advocate, and so I did all of this with open source software. Omniscape itself is open source, developed by the Nature Conservancy, and all my maps were made in QGIS, and we're using open layers basically to serve out all this data over the web. So that everything that I showed was based on open source.
And one last question. Has the model data been compared to any real world data to verify the model?
No, no, it is, but that is important to note. It is a model. It isn't reality. It's a model, and so it is important that we have some field verification at some point. So that's where we would like to engage, I think, scientists at some point to do more detailed looks on the ground in some of these watersheds and to look at some of these linkages and see what's there.
Great.